Do you guys see it?
Fantastic. Okay. Andrea, thank you so much for joining us. I'm really excited about this talk. I think that from what I've read, it seems like you exist in sort of the space that I'm very excited about, which is like this intersection of actually hacking things that people care about the security of, and also sort of understanding some of the theoretical underpinnings of why these hacks are possible and mechanically how. So I'm very excited about this talk. And with that, the floor is yours. So thank you for joining us.
Thank you very much. Thanks actually for inviting me to give this talk. So like, yeah, today I'm gonna present you like just a small part of the research we have done in microarchitecture attacks. And in particular, I'm gonna focus on a use case that we found on how we can apply speculative execution attacks to bypass memory safety mechanisms. Before starting, a little bit of myself. I'm currently now like a researcher at IBM Research in Zurich. Before I was like a PhD student at Northeastern System Security Group with Engin Kirda. Yeah, like my focus is on microarchitecture attacks and also like operating system hypervisor security as a side thing. Okay, so before going into the details of is it good? Before going into the details of the talk, I need to basically give a small introduction on what transit execution is, and just like very briefly. So transit execution, it's the type of execution modern CPUs basically applies when they apply some optimization to the execution of a piece of code, and they generally involves like transit instructions. These are a sequence of instructions that are generated, and they cross the pipeline and gets executed by the CPU, but their outcome is kind of unknown until the very end. And so there are two possible ways in which like the execution of this instruction goes. One is that the instruction will retire, and so the side effects will be architecturally visible. So our application running at the architectural level will see what these instructions that the CPU has generated have done, and they will be able to use the results. However, there are situations in which like the CPU employs these instructions, but in the wrong way. And so what happens is that these instructions by the end will be squashed by the CPU. This means that the CPU will try to roll back whatever has been done in the speculation window, and will try to pretend that nothing happened. So our application running at the architectural level will not see what's going on in the microarchitecture and will not see these side effects. So this was true until 2018, when people figured out that that was actually not the case. So and that's where transit execution became like an attack surface, because this type of rolls back most of the changes, right? But not all of them. So there are some side effects left behind that some program at the architectural level might be able to see through some attack. So let's now have a look at how these type of attacks using transit execution are built. So as I said, there are some transit instructions that are generated by the CPU. We assume that these transit instructions will access a secret of some sort that we are interested in, and they will leave some side effects in the microarchitecture that it's function of this secret. And then we assume that there is going to be like some side channel or cover channel that will allow like an application running at the architectural level to leak these side effect from the microarchitecture. So basically retrieve this information. So that's like the threat model for this type of attacks is the following. So we always have like a victim program that basically is holding a secret, right? And then we will have an attacker program that is under attacker control, which will try to leak this secret using the CPU. The way these programs are running can vary. So the attacker program can be also part of the victim program in case they are running in the same address space. There are situations in which like the two programs are running as a sibling thread, and then there is also a situation in which the attacker program is a complete different program in a different address space. So let's have a look now at one very small example of this type of attacks in practice. This is Spectre version 101, which was introduced by Kiriaski in 2018. It's also known as the speculative buffer overflow. So this type of attack exploits a piece of code such as this one, right? So we have one array of a specific size, and then we have a bounce check on this array. And within the bounce check, what we do is like we perform a store of a value inside the array. So this is the situation of this particular function in how it looks on the stack of the program. And so when we execute this piece of code, right, and we hit this instruction here, we have a comparison. And if you assume that the size is not, the size of this array is not cached, the CPU, modern CPU, will employ speculative execution. So it will not wait for this value to come all the way from memory, because it's a very slow operation. So they will try to guess what's the result of this comparison. And if you assume that we have been running this code previously a few times with X inbound, the CPU will say, okay, it's going to be inbound also this time. And so what is going to happen is that the CPU will proceed and will perform this store. And this store will be speculatively executed. So it means that the side effects will be in the microarchitecture, but they will not be architecturally visible yet. And so what is going to happen here is that if we shape X such that we are able to target, for instance, the return value on the stack, as you could see here, this value is temporarily placed instead of the return value saved on the stack. So if this is, so far is not yet an attack, but if we assume that the speculation window allows us to also reach the return here, what is going to happen is that if we are able to speculatively execute the return is going to use whatever value we stored on the stack instead of the return value, the saved return value. And this gives us a very powerful primitive, which we call a speculative control flow hijack. So this is one of the strongest primitive and allows us to basically redirect speculative execution at an arbitrary location within the address space of the application. And so to complete an attack, we assume that at that location, there is going to be like some side channel gadget that allows us to send the signal inside the microarchitecture. So we'll see later like an example of this like side channel send gadget. So when we started our research in this particular area, we looked at other ways what are all the ways to achieve this very powerful primitive called speculative control flow hijack. And we basically try to summarize it in this graph. So here we have, the first way that was presented was through microarchitectural components. So the idea here is that by poisoning microarchitectural components such as the RSB or the BTB, so the return stack buffer, which is the component used to predict returns when the value on the stack is not readily available, or the BTB that is used to instead predict indirect branches whenever the target of the indirect branch is not readily available. So if we are able to inject some values in these microarchitectural components, these are components that are shared between all the processes that are running on a specific CPU. So if our attacker is able to inject some values there by running before the victim, and then the victim is going to go and use the same CPU, it might use the value that was left behind by the attacker. And some previous work already showed that you can achieve a speculative control flow hijack through basically the poisoning of these two components. However, there is also the other way we can poison and use architecturally visible elements, which are memory locations and registers. And so what we can do with that is like we can either speculatively override them if the store or it happens like speculatively, or if the store happens architecturally. And what we can overwrite are either the backward or the forward edges. Okay, so this whole category, we call it SPEAR, so speculative architectural control flow hijacks attacks. And as you might have noticed, one case was already covered by previous work, which is the Kiriansky example that I showed at the beginning, in which we would speculatively override a backward edge. However, there are like other free cases that nobody like looked at before, and we did it in this work. So, okay, so let's consider one case. Let's consider the architectural override of a backward edge. That's just a fancy name to basically say buffer overflow. In a buffer overflow, what we do is like we architecturally override what a memory location, so it's an architectural element, and that is a backward edge because we are overwriting a return value that is saved on the stack. So ideally, if we have already that primitive and there is nothing preventing us to architecturally exploiting that, then we can just simply do the buffer overflow. But so there is no need for bothering with speculative execution. But if you assume the use case in which the application has the stack smashing protector deployed, maybe we have this primitive, so we have the buffer overflow happening in the code, but that overwrite is not usable for in the normal exploitation. So in our work, we looked at, can we do something with speculative execution, even though in the normal type of exploitation is not possible anymore. And so we looked at ways to basically bypass these various use cases. One is the stack smashing protector. Then we looked at the CFI mechanism and also like the memory safe languages. So what can we do with these attacks? So these attacks are different, like than, the speculative execution attacks have a different goal than normal exploitation. So if we have a buffer overflow, we try to, spawn a shell or do something like on those lines. But if we have a speculative execution attacks, what we try to do is like to reach in locally arbitrary memory read. So that's our main goal. So we are trying to leak a secret from the application. And generally, we have seen that the steps to achieve this are the following. So we always have like an initialization phase in which we initialize all the elements of the side channel, or in case in our specific case, we also had like some ROP gadgets, so we had to initialize them. And I'm gonna show you later what I mean with this, as well as we needed to find what we call an eviction set. So ideally, we need to trigger speculative execution in one way, and we need to be able to basically identify the cache location in which the particular element we want to evict is, so that we can evict it from an attacker-controlled program. Then we will have like the attacker sending the malicious input, which will basically trigger the override we talked before, which will trigger the spear code inside the victim. And we assume that at that moment, speculative execution will be employed by the victim, which will then execute a series of ROP gadgets, can be one or more, which will build this side channel send, which will send the information through the microarchitecture to the attacker. And everything is done in parallel to this eviction loop phase that takes what basically is trying to keep a certain piece of information outside the cache. And this allows us to basically trigger speculative execution inside the victim context. And we will see in a bit exactly what I mean with this. So now let's have a look at the use case, how we bypassed the stack smashing protector. So the code, the spear code that we looked at was the following. We have a mem copy, right, that allows us to perform buffer overflow because we control the source buffer as well as the size. So the attacker controls that, and that allows us to basically overflow this buffer with this local buffer. Ideally, we know if we compile this code with the stack Canary, the compiler will inject a piece of code like this one. So it's gonna, of course, we generally don't see it because it's automatically introduced by the compiler. This is just like to give you an example. So before returning the compiler injects like a check if the canary is okay. And if it's not okay, it's going to abort before performing the return. So the attacker will never achieve the return control flow transfer. I mean, or the control flow transfer through the return instruction. So when we execute this, we get the buffer overflow through this copy. And then if we assume that we are able to execute this piece of code with the canary that is checked not into the cache, this will trigger speculative execution from inside this piece of code. And what happened is that we might actually be able to hit this return here. So this is the actual piece of assembly that the compiler will inject. And as you can see, basically, there is a comparison of the value that is generated when the application starts up compared to the value that is on the stack. And if the two are different, basically, this stack check fail is called this function to fail. So ideally, if this location in memory is not readily available, this will trigger speculative execution. So when we hit this return, what is going to happen is that we are going to gain, we're going to use as a backward edge whatever value we were able to overflow and write on the stack. And this will give us this control flow hijack primitive that I was mentioning before. However, like one of the issues with this type of attacks is that we need to achieve this canary eviction. So this generally the canary is a piece of code. I mean, it's a piece of memory, sorry, that is used very frequently. So we would expect it to be always into the cache, because every function that uses the canary is gonna load this value from the TLS, like a section of the binary. And so we expect it always to be in the cache. So we need to be able to achieve the eviction of the canary to perform speculative execution in the right moment. So to in a fake scenario, what we would use would be like a CL flash operation that allows us to basically clear the cache of a specific cache line. However, that is not very realistic, right? Basically in a real example, in a real end-to-end attack, you cannot use CL flash because you need to find it in the code, and that's generally not introduced. So we need to find a canary eviction technique to apply this. And this basically introduced our first step, which is this find eviction set. So what we did was like, we generated from the attacker point of view 2 different programs. One program is holding a canary. So this second attacker program is compiled using the stack canary. And what we did was we tried to, from the first attacker program, we tried to load various eviction sets in a loop. And from the second attacker program, we will time the access time for basically reading the canary. And as I said before, the canary is generally inside the cache, so all the reads we will do are generally very fast. However, there is the case in which the second attacker program, by creating a noise on the last level of cache, will be able to evict the cache line that is holding the canary for the second attacker program. And whenever we find this situation, the second attacker program is gonna basically experience a slow read of the canary. And whenever we find like a slow read of the canary, the second attacker program, it will send to the first attacker program the information about the LLC slice and the cache set. So it's gonna tell like, look, you were able to evict the stack canary by evicting that specific eviction set. So you should not keep looking. That's your cache set that you are interested in. And so once we found this LLC slice and LLC cache set, the trick here is that the canary is initialized whenever the program is first started. But if we exec a new program from the original program, the TLS location is not regenerated. So ideally, like once we found the eviction set, if we exec the victim program from our attacker program, the location of the canary is not going to change. And in fact, pretty much what we found is that in the way the page array used inside the operating system, this is actually what happens. And so now we are in a situation in which we are running the victim program, which is compiled with the canary, which is the same location of that we know. And the attacker program that is running in parallel has all the knowledge to keep this canary outside of the cache. And so this fourth stage that I was talking before, this eviction loop, is performed by this first attacker program that keeps loading his own eviction set, which will create noise on the last level of cache. And this noise will basically evict whatever is in there, which is the cache line with the stack canary. So like to finalize our attack, of course, once we got the spear code to be triggered and we are able to trigger also speculative execution, we need to finalize the attack, which means that we need to access the secret and we need to send the secret through some side channel. And what we did in our attack, we basically build a sequence of ROP gadgets that will replicate the Spectre V1 double array access, which is a very powerful type of gadget that to perform this side channel send. So we basically found the following gadgets. These are like the 4 gadgets we used. And these were found in various libraries that the victim program was using. And so during the buffer overflow, we would overflow the stack. And as you will do in a normal buffer overflow, we could save all these ROP gadgets addresses on the stack. And so once we got the first speculative control flow transfer, then we will start to execute all these gadgets, which we saved on the stack architecture. And so the first gadget was actually loading the victim secret we were interested in. The second gadget will basically take whatever we read, the byte we read, and basically offsetting in our side channel array. And this is pretty much what we needed to do. Basically, each cell of the array is actually 256 cells, and we wanted to make sure that we will not 2 hits in the side channel array will not end up in the same cache line, because those hits will not be able to tell them apart, pretty much. Then the third gadget will basically bring this index that we calculated and put it in the actual array. And finally, basically, we perform the load using the index we computed. And so only one of the cells of this array, basically will be brought into the cache. And that's based on the secret byte that we retrieved initially. So one catch here is that this side channel array should be shared between the attacker program and the victim program, because otherwise the attacker program will not be able to see the side effects happening. And so what we used was actually in Linux, for instance, you can use the shared libraries. If both the attacker and the victim loads the same shared libraries, the shared libraries, given that they are loaded only once, so the physical page is actually loaded only once, you can use that as a side channel array. So we made sure that we took a piece of code in one of the libraries that was not used by neither the victim or the attacker. And we made sure that that side channel array was not into the cache, and only one piece of the code will be loaded using this ROP chain. So and then like the final stage, the side channel receiver basically happens in the following. So we have the payload. The payload will trigger the vulnerability in the victim program, which will send again the side channel send to the array, the shared array. And then the attacker will basically just go and time each one of the cells of the array, and only one of them will be faster than the others. And that was the byte we actually retrieved. And in our end-to-end attack, so we built this attack on a buffer overflow that we found in libpng, which was mitigated by SSP. So the origin buffer overflow was not exploitable anymore because there was like the stack canary. And we used as a shared array the libp thread, which was loaded in both our attacker program and the victim. And so and then of course by reiterating this attack, we will be able to basically retrieve 1 byte at a time. So our results show that we were able to basically leak at a rate of 0.3 bytes per second. And we tried this on multiple architectures, Skylake and Coffee Lake. And we also we had all the mitigations for Spectre enabled, but basically we're not applying in this particular scenario. Of course, in the paper, we also had like a little bit more discussion about some of these stages, and we can discuss it also later. So what are the takeaways of our work? It's basically that we showed that the Spear is able to bypass the memory safety mechanism. And in our work, we also target CFI and some of the memory safe languages. And we showed that these type of attacks can be applied also there. And the takeaway here is that basically speculative execution has changed the threat model, even for modern mitigations. So we need to basically be able to rethink the design of some of the mitigations we have in place to account also for these new type of attacks. We show that these attacks are, they are complex. They have they have quite a few stages. And there is a lot of technical details that should be taken into account, but we also show that they are practical. So we were able to practically build an end-to-end attack. And also we believe that, so far in this space, there's a lack of tools, automatic tools to find certain characteristics of the attack. But by building those, I think we will be able to optimize the success rate for each one of the stages I showed, and make it even more practical. We were also the first one to show that the speculative ROP is actually possible and is actually usable to build side channels and gadgets, and in particular the Spectre v1 gadget. So one thing that should be that was clear since the beginning of these attacks is that the Spectre v1 gadget, or the very first attack that was presented, is actually not a very common code pattern. So finding the double array access in a normal code is very hard. It's almost impossible. And people have been trying to find those, but they don't really exist very normally in the code. And in fact, for the exploitation of Spectre v2, what was done in the only POC that was available was actually injecting one using the JIT compiler inside the kernel. Because they couldn't find one particular construct. So with speculative ROP, we can actually build it, piece by piece. So we don't need to find the whole gadget in one go, but we can build it, and that makes it much easier to basically just finding it in the code. And finally, we believe that this type of attacks will be, they are very hard to eradicate because they are not leveraging a bug inside the microarchitecture, but they are only leveraging a performance optimization that works as expected. So there is no violation of the contract between the hardware manufacturing and how this optimization actually works. And so it's very intrinsic on how we should change our way of writing code. And so we need to change that so that we will not basically trigger these scenarios. And so we will like with more tools that will be available, these attacks will become more practical. And so they will become even more of a challenge, try to fix them in the future. Yeah, and this I conclude. We can also discuss a little bit of other parts in case a question come up. But okay. Some references.
Cool. Thank you very much, Andrea. Looks like both Giorgio and Matt have questions. Giorgio, why don't you go? Or are you clapping? I'm sorry, this is a clap emoji. Okay, I'm clapping too. I appreciate it. I'll start us out with an easy question, and then other people can jump in. It's interesting to me that you mentioned like software as an approach to trying to defend against this. Why wouldn't you do the obvious thing of just saying every chip should have a little tiny chip on it that doesn't do any speculative execution, and that's where you do anything where you care about the security? Like, what's wrong with that kind of moral stand?
So, I mean, that, I mean, one of the main issues is that you are relying on the fact that the programmers will do the right thing, right? So they will be able to disjoin whatever is, secure from whatever is, can be executed insecurely. And as well as like, you will need to find a way to send, or better, like whenever you generate some secret, this should be generated by this chip you mentioned, right? And kept there for the whole existence, its existence. Because the moment you pull it out from the chip, then if you find like some triggers that gives you speculative control flow hijack, you can still access that secret if it's somewhere in memory, right? And so it makes it the moment you require someone to basically rewrite a piece of code, then makes the whole mitigation way harder to be employed, and is the basically handling a secret through automation, like through the compiler. Let's assume that you instead of asking like a developer to apply changes to the code, you try to do it automatically through a compiler pass, right? The compiler pass should know what the secret is in your code, and that is very dependent on the type of the semantic of the code you're writing, and so you're still relying on the developer telling you what the secret is in a way, right? So that type of approach is will always will always not be complete in the way you can apply it. And I mean, there is a huge amount of work that has been done from the microarchitecture community, of course, to fix this in hardware. And there are like two main approaches, let's say. One is to basically change the cache hierarchy, which they basically, what they are trying to do is like they try to avoid these side effects through the cache. However, that is only preventing for instance a spear attack build using a cache side channel. But we know that there are many other more cache side channels, side channels in the microarchitecture. For instance, there is like you can use port contention, or you can use the branch target buffer as a side channel. And so you fix basically the caches, but you still have like some other like channels that people can use to basically leak data. So that is not a complete approach for defending from this type of attacks. There is another line of work, which is instead of trying to detect unsafe operations happening in the pipeline and forbid those, based on some policy or schemes. And those are more promising in terms of like preventing almost the majority of these attacks, and they've been shown through like some simulation. Like, but the only problem with those is that they only are gonna protect future iterations of the CPU, right? But we know that the world is very slow in terms of updating hardware. We are still, I mean, there's people still running, I don't know, Windows 95, right? So on very, very old hardware. So the idea is that that is good approach, but there is going to be a lot of legacy hardware around for many years that will be still vulnerable to these attacks because they will not be able to employ those changes. So yeah, so there is like some work that people are trying to do through compilers to inject, for instance, L fences to stop speculative execution whenever they think there is like an unsafe condition. But also it's based on heuristics, and the heuristics can be correct or can be overdoing. So you're paying more overhead overall than you should. Or sometimes, you know, the people are more conservative, so they inject less of these masking or L fencing. But in that case, you are basically still not protecting completely the application. So it is a bit of the trade-off there. Yeah.
Quite a generic question, but just to get a better idea of the context, how relevant is the speculative execution to like recent CPU performance? Like, what are we losing if we consider removing it completely?
So you face, like, I think I mean, there are specs that the people have employed, but like you basically go back of 10 years in terms of like performance by disabling it. Because if you think about it, like the original way of improving performance in hardware was to basically pump up like the frequency of the CPU, but that was only possible up to a certain, you know, frequency, because then there is like the hardware limit of heating dissipation. And so people started to work on, you know, this parallel execution and then optimization such as speculative execution. And those were actually most of the performance is achieved. And every iteration would add some speculative parts or speculative component. And there are nowadays like a lot of situations in which the CPU will still speculatively execute without waiting, and this can be done on a lot of situations, like between so by removing all of that, yeah, you basically go back of 10 years. I think it's a I don't know, 100 times slow down or something like that. And in fact, whenever like the first approach came, which was basically L fencing everything, people were not willing to pay that amount, of course, because even if you do lightly, you might end up with a 10% slowdown, especially if this condition happens in a loop. Speculative execution is pretty heavily done when you have loops, and so that will cause your loop to become like because you stop also other type of internal optimizations when you stop like speculative execution, and so you basically lose a lot.
And another, like, maybe dumb question, but again, just to get a better context, it seems that to get the attack to be effective, the speculative window should be somehow large. At least that's what I was kind of getting from the previous slides. How large are these speculative windows, and is there any advantage in reducing the size? Like, is that like a easy fix that someone can just do, or are we losing a ton of performance by reducing the size and that, we're back to the square one?
So, so you do lose a lot of performance if you squeeze the window, because then you are not optimizing the execution units of your. So the idea is that the theoretical maximum of the speculation window is the size of this reorder buffer, which is the buffer where all the micro operations that are coming from the front end of the microarchitecture ends up. So they arrive in the reorder buffer, and then they are scheduled for being executed by the execution units whenever all the parameters are ready to be basically passed to the execution port as well. And then the result of that is sent back to the reorder buffer, and basically the instruction basically change the state and becomes like executed and waits to be committed, basically retired. And the idea is that while you are speculative executing, you're adding more micro operations to the reorder buffer, and these instructions will be executed out of order. So if there is no data dependency, and there is like one line of instructions that are waiting on a specific piece of data, but down the stream of the instructions, there is some instruction that is completely unrelated. Those will be executed, but they all will be then retired in order. And that, keeps the semantic correct of your program, which is also the one that basically makes sure that if there is some misspeculation, is going to be figured out when the instruction that was generated the speculative execution will basically will verify that there was a misspeculation or not, and will just trash whatever is in the reorder buffer that was generated from that event. So by shrinking the window, you might end up like reducing the capabilities of your architecture in terms of how many instructions per second you can do, because of course there is like a gap, not a gap, but a sort of a cap of instructions that you can execute. That is like how many. So if you have like a huge stream of instructions of the same kind, then the bottleneck is the fact that you don't have enough instructions, enough execution unit for that type of instruction. Because, for instance, if you have a series of mobs instructions, there are only few execution units dedicated to mob. So you are gonna basically optimize only, or use heavily just those ports, and the other will be empty. So the idea is that if you instead have a more heterogeneous like sequence, then you will be able to optimize all the execution unit. And so you need like a large reorder buffer to make sure that you can do that. Keep having like different types of instructions in the stream.
With the side channel attacks, how much do they have to be customized to the specific chip? Like, do you have to rebuild the same attack over and over in order to get different chipsets, or do you find that the timing windows are pretty similar across different architectures?
So one thing that like there are some characteristics that depends from the various like CPUs and boards you're attacking. One thing that you need to always do is calibrating. If you're using like a a cache side channel, the access time for the cache is really dependent on the type of cache your system has. So sometimes you have like a certain latency for a cache hit, which might be very different from the various architecture based on how fast the buses are and so on. So you need to calibrate that, because otherwise, if you always use like a fixed threshold, you might end up to not see the difference between the cache hit and the cache miss, which is what you use to basically retrieve the data. So that is one. In terms of like a window or a type of misprediction, so for instance, like internally, when you try to poison like some of the microarchitectural components, in some cases you might need to you might be able to poison with with less iterations. For instance, the branch target buffer on one architecture, but for another architecture it might take longer because for instance, the newer branch target buffer are able to keep a longer history of all the branches. So you need to make sure that you have a longer history between the attacker and the victim that should be the same. So to make sure that what is used by the attacker is going to be used also by the victim, and that is a little bit more dependent on the families of like I don't know if you on Intel, I don't know if you are on a Broadwell or a Skylake or a Tiger Lake, things are different in that case, and that you need to play a little bit more. And there hasn't been much work to characterize this. And I mean, there were like papers, reverse engineering some specific components on old hardware, but this work hasn't been done on more recent ones. So there is no like a perfect recipe when you move your attack from one to another. You basically need to experiment because basically the functions that these components are implementing keeps changing. In a way, because they are getting better, they are just adding more history, they are just considering history in a different way, and there is no details of these implementations because it's all intellectual property of the manufacturer. Because yeah, you just need to know that they go faster and they do that on behind the scene, but there is no interest for them to really reveal it to the programmers, right? So does this answer your question, or?
Yeah, absolutely. Thanks. Matt and Kai, if either of you have questions, I want to make sure you feel free to jump in.
No, really cool talk. I'm sort of curious if this all works even when you have, so especially with the use of ROP, does this all work on something like Windows if you have control flow guard? I know that's like not quite a software solution. This is like a hardware issue, but I'm wondering if there's like something in software you could use to like detect something like this. And I ask because I have no idea.
So ideally, there is no way to know because everything happens transparently in the microarchitecture. So your code will never. So what you detect is of course the architectural override, because that is going to be visible. That is visible. So whenever we do the, let me just go back briefly. So when you do the buffer overflow in the that one, like you're architecturally changing the stack values. So those are these this override is actually gonna stay architecturally because the mem copy is architecturally executed. The idea is that the program will fail eventually, but before failing, we will be able to hit this return and perform our instructions.
Got you.
Then we don't care if the application crashes or
because we already got our code execution. Yeah.
Exactly.
Who cares?
So the side effect is already sent to the microarchitecture, so the code now can be terminated. And then since we consider, of course, a local attacker in this case, the attacker can either restart the application if it's a local one, or if you are, for instance, on a web server, right? The web server, if you cause like a crash inside the worker that the web server is spawning to serve your request, the web server will still be available to answer you again. So
and once you have code execution, you can always just like repair the stack or repair whatever you need to. But yeah, I was just wondering if this is like detectable, but it really seems like from what you're saying, like this is like either super expensive to detect at scale, or just like not really feasible to detect. Because once you have that code execution, you can repair everything you need to, right?
So, but the idea is that you will not get code execution, right? Because the application terminates.
Okay. So is it just reading or just adding?
Yeah.
Okay, I'm sorry, I misunderstood. Thank you for the clarification.
Yeah, no, worries. So basically, like the idea is that the code execution you will get if you get, if you can, if you don't have like the canary in a way, or you find another way to basically use the memory corruption vulnerability. In our case, we assume that you have that primitive, but you cannot really gain, the code execution, at least the architectural code execution, because there is a canary that terminates your application before you get there. But you still gain like some code execution at a speculative level, which then allows you to leak some information. And the idea is that this type of application that we target should be an application that either you can rerun on your own, or is automatically spawn again if you are doing it remotely. Because of course, so in a way to detect this type of attacks, you might see, in particular for this architectural override, you see a lot of crashes. So that's your way of like, because the attacker needs to, if you have like a long sequence of bytes that you want to read, you need to repeat the attack for the amount of bytes you have. Also, because of the cache properties, there is a little bit of based on how well you can prime the cache, then your signal will be better or worse. And based on how is your signal, you might need to repeat this attack many times to make sure that you properly read the value. So you need to do some statistical analysis on what you get as a result. Mm-hmm. And that is prone to be visible because of the moment you repeat the attack, you basically are crashing the application. For this one, if you instead go to the basically if you instead do the speculative override, in that case the program will not crash. So you will have this primitive. You will be able to reiterate the attack without crashing the application, and that is like less, of course, way less noisy from that respect. So these architectural speculative override or backward or forward edge are much more stealthier in a way than the other two cases.
And then just as a follow-up, it seems like a really cool place to use this would be in a situation where you have like multiple VMs running on the same bare metal. Have you tried using this to like send and receive data, or just honestly read data between VMs?
So the idea is that the two VMs should have like some shared memory, of course. Which due to the hypervisor and so on, I am not sure you can achieve that very easily. So one idea is that you need to still be able to prime some of the so in this initialization phase, right? You need to be able to prime the memory of the other VM, and that will be tricky because you don't have access from one VM to the other. You will be able maybe to perform the eviction because of course you are sharing the last level of cache if they are co-located. But it's going to be very tricky to basically get these two phases going. And without these, you basically, your side channel will be very noisy. So it's not impossible, but like there are other assumptions that you need to have in that setting for sure. So we haven't tried it personally in that scenario. But for instance, if you assume like a shared machine with like many users on the cloud and stuff like that, yes, then that's basically the perfect settings for these type of attacks. Because one of the things of if if you're able to, for instance, like if the two VMs are disjoint completely and they are working on two different cores, then the attack is not possible, because if they are basically having also the LLC in a different LLC sharing and so on. So
Andrea, we should probably wrap up because we've taken up an hour of your time, but this was super cool. Thank you so much for joining us. If people have questions or want to learn more about your work, should they email you? Should they contact you over Twitter? What's the best way to get a hold of you?
Yeah, Twitter, email, anything works for me. Also, if you guys want to, like the link here on the bottom of the slides is our blog from my group, and we are trying to, also go a little bit more into details with like some blog posts related to what we are doing, not only this but also other stuff. So if you want to keep up to date with this type of work we are doing, just follow also that.
Fantastic. And I'll post a recording of this online, so if people want to revisit anything, they'll be able to. And yeah, thank you again, Andrea. This was absolutely phenomenal.
Thank you very much. Thanks for the invite and the attention, guys. Thank you.
Okay, adios.
Thank you. Thanks, Andrea.